Teacher Carlos Plain of Durham School states, "I went through my entire time on Earth empowering and expressing a hypothesis of the universe. In addition, at last, the hypothesis is being tested. I welcome that since that is the way we push ahead. That is how we gain ground in science." The James Webb Space Telescope is upsetting an exceptional measure of what has been seen as truth in cosmology. For the new year, another ultra-deep picture shows that we have serious goofs in cosmology. The telescope, which should show us the fundamental stars of the universe, is evolving into a foe of the past perspective. Furthermore, it may present to us a thoroughly astounding science. Not all experts are grappling in dread at the new realities. Other well-educated specialists welcome the advancements since it has for a truly long time been sure that something was the matter with our old speculation. The deviation in the assessment of the headway speed of the universe alone should have shaken specialists' perception ultimately in the past. Yet, bringing everything into account, they stuck to old theories. The cosmic microwave background radiation, CMB, considered the most settled light in the universe, was made something like 380,000 years after the Big Bang, right when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Researchers call this interaction reionization, which made the universe transparent to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were dealing with another kind of radio-receiving antenna technology. This revelation was for a long time seen as possibly the strongest piece of proof for the hypothesis of the old Big Bang, earning Penzias and Wilson a Nobel Prize and a certain spot in the history of astronomy. The CMB most reasonably offers a viewpoint on the early universe, with little temperature contrasts providing essential data about the conditions not long after the Big Bang. Theoretical scientists included the CMB as a solid scratching of the fundamental assessments of the material universe to check the headway speed of the universe, among other things. The cosmologist Edwin Hubble had already settled this in the late 1920s, tracking down that faraway world's retreat from us and that their speed is corresponding to their distance. Today, these perceptions are known as the Hubble law or the Hubble constant. Hubble didn't have the high-level evaluating systems available many years after the fact at the point when the CMB was found, which led to a recalculation of the expansion rate. These were generally lower than Hubble's original figure. Later, experts recalculated the rate utilizing type Ia supernovae as standard candles, providing stable light that could be used as a solid measuring point. The assessments within the CMB yielded an expansion speed of around 67 kilometers per second per megaparsec, while estimates utilizing infinite blasts yielded around 74 kilometers per second per megaparsec. What does this discrepancy in deciding the advancement speed of the universe truly tell us? Did you know that this goof has been known since the 1990s? Since that point, analysts have known, or at least thought, that something may be the matter with the examination of the CMB, the appraisal strategies, or the possibility of the universe's extension. The anomaly between the observed and anticipated values of the expansion rate is referred to in science as the SAA pressure or Hubble strain. The ramifications of this strain are enormous, showing that fundamental bits of how we appreciate the universe may be damaged. For a long time, specialists were bewildered. Since the James Webb Space Telescope went into action, it has outfitted experts with stunning information that may now uncover data on the issue of the expansion speed of the universe with systems so old and mature that their advancement should have begun hypothetically before the Big Bang. This is toppling old cosmology. Scientists no longer discuss mistakes or appraisal contrasts. They discuss the emergency in modern astronomy. Not only could the expansion rate be off, but the entire idea of expansion or the Big Bang itself is being called into question. Pictures from the telescope give proof of a universe totally unforeseen from what we have long thought. The SAA pressure was the chief scold to specialists who still have faith in old theory. Now, they face an issue. Do we in fact understand the universe? Different researchers stand on the remains of their once brilliant source of both revelation and torment, researching space with fear and wrestling with what they find. Taking into account the emergency in science, we should ask ourselves, what do we in fact know about the universe? To answer this, we truly need to understand how science functions. Speculative experts use an intricate arrangement of mathematical models, careful data, and wise reasoning to draw conclusions from the general to the specific. Their understanding comes from a blend of discernment attributes, significant outcomes, and speculative appraisals. The term hypothesis alone shows that these are advancements and contemplations, not through and through bits of information. The primary critical data we have are the photographs telescopes provide, the sound waves and radiation gathered with radio telescopes, and the most recent data from neutrino surveying systems or gravitational wave markers. With the James Webb Space Telescope, we now have an instrument that can split the light into individual frequencies and examine it in amazing ways. Webb can show us the fundamental parts of systems in the early universe billions of years ago, how much mass they contained, and the number of stars present. It can also track the shape and course of a galaxy's development. Webb, however, has limitations. For example, it can't always totally decide whether we are seeing galaxies or instead black holes with gigantic gravitational forces that shine as brightly as a galaxy. We must face the reality that our science has long accepted an excessive number of potential results as facts, while excusing collective clarifications. Research has for a while been certain about its accuracy. The most recent disclosures from the James Webb Space Telescope are fundamental signs to supplant speculations with new insights, as has occurred generally in science. Experts are eagerly expecting the new discoveries, which are suddenly amazing and different. Specialists are attempting to develop new explanations. The new revelations shake the underpinnings of our current science, disturbing numerous specialists. The current models of real science are still generally founded on Isaac Newton's laws from the 17th century. His laws of motion and gravity were the foundation of our understanding of the reality of this world and the universe for quite a while. Newton's principles explain the development of things under normal conditions and function particularly on Earth. However, in space, his theories required advancement, generally completed by Albert Einstein in the mid-20th century. Einstein's special theory of relativity, published in 1905, changed how we interpret reality, showing that realities are relative to each other and rely on the observer's movement. His general theory of relativity, published in 1915, extended this thought with mathematical descriptions of gravitational qualities based on the curve of spacetime by masses like stars or galaxies. Einstein's principles and ideas were significant in numerous areas. However, he also recognized their limitations. He knew his theory would never fully describe the universe and longed to see a unified theory, which he never achieved. No other expert has reached this stage either. Wouldn't it be fascinating to know where it lies? Michio Kaku, a prominent astrophysicist from the USA, said in an interview that addressing this issue would undoubtedly win a Nobel Prize. Could we investigate whether the experts might have missed potential misinterpretations or whether our telescopes are to blame? Dark matter and dark energy are at the top of the suspect list for the primary causes of the cosmological emergency. Our evolving models of the universe integrate ideas that dark matter and dark energy make up around 95% of the universe. However, neither has been clearly observed, and their confirmed presence has never been demonstrated. They likely don't exist in any form or shape, requiring elective clarifications for the universe's expansion and the dynamics of galaxies. On the other hand, they could have properties we don't yet understand. One idea is that the true properties of dark matter and dark energy have changed over time, possibly showing some form of evolution. Gravity is another theory to be tested. This force, which creates attraction through mass or curvature in spacetime, has not yet been fully explained. The concepts of spacetime curvature, which stem from Einstein and have been customarily supported, may require revisiting. We can't rule out the possibility that gravity has unanticipated properties or that another force is responsible for the gravitational attraction between objects over time. A few constants have been established in cosmology and astronomy as universal principles. The study of the universe has always been a journey defined by our constant quest for understanding and discovery. From ancient human civilizations observing the stars to modern space telescopes investigating the depths of the universe, each step toward improvement and theory has uncovered new mysteries while testing established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, remains as a beacon of our scientific advancement, promising to change how we interpret the universe's origins and development. Launched with remarkable capabilities, JWST represents a leap forward in observational space science, designed to look further into the universe than ever before with extraordinary accuracy in analyzing radiation. The CMB, often referred to as the glow of the Big Bang, offers a perspective on the universe as it existed just a short time after its first interaction with light. This ancient form of radiation carries fundamental information about the universe's early conditions, including its temperature variations, which are crucial for understanding the evolution of galaxies and large-scale structures. The difference in the observed values of the Hubble constant, known as the Hubble strain, has been a subject of long debate. It suggests that something is amiss with our fundamental understanding of the universe and its early formations. Disclosures challenge traditional theories and require a reassessment of whether our viewpoint on cosmic evolution is inherently flawed. New insights may reveal hidden parts of the universe's creation, raising questions about dark matter and dark energy, two unexplained components that make up the majority of reality. The advancement of science relies on the ability to reshape our hypotheses based on new data. Webb's mission embodies this pursuit. Its discoveries will serve as a foundation for future cosmological discussions and should open new perspectives on the universe's mysteries. The future of cosmology may witness significant changes, leading to major implications for how we interpret the universe, from the Big Bang to the ongoing processes that define its future. The answer to the greatest and endless question may lie beyond our current knowledge, and Webb's observations may finally be essential in uncovering new insights that could reshape how we interpret reality itself. The way forward for cosmology and space science is filled with potential. Each groundbreaking observation and piece of insight from telescopes like Webb brings us closer to answering the most significant questions humanity has ever posed. How did the universe begin? What is its ultimate destiny? Are there other forms of life out there? Or are we alone in this vast universe? These are questions that may one day find answers, and the James Webb Space Telescope is at the very forefront of this grand endeavor. The fate of cosmology will likely involve a combination of new technologies, refined theories, and profound revelations that continue to push the boundaries of what we know. As we venture further into the unknown, one thing is certain. Science, like the universe itself, is always in a state of constant expansion, driven by the quest for knowledge and the wonder of discovery. The journey of understanding the universe is an ongoing quest for knowledge that constantly reshapes our perception of reality. As we push the boundaries of our scientific capabilities, we begin to realize that many of the fundamental theories that once seemed solid are, in fact, open to reinterpretation. The advancements in space science, particularly through powerful telescopes like the James Webb Space Telescope, JWST, have opened new avenues of exploration that challenge old assumptions and suggest that the universe is far more complex than we had ever imagined. The observations made by JWST, which has the ability to peer into the distant past of the cosmos, are yielding stunning new insights. The telescope is providing unprecedented views of galaxies that formed just after the Big Bang, helping scientists understand how these early structures developed and evolved over time. By studying the oldest galaxies, we can gain a clearer picture of the conditions that prevailed during the universe's infancy. The ability to analyze light from these distant galaxies with such accuracy offers a direct window into the cosmos at a time when the universe was very different from what we observe today. However, the more we observe, the more questions arise, prompting us to revisit established theories and consider the possibility that some of the laws we take for granted may need to be adjusted. For example, one of the most profound implications of recent discoveries is the potential reevaluation of the standard model of cosmology. The data from JWST and other modern instruments suggest that our understanding of cosmic inflation, the rapid expansion of space just after the Big Bang, might be incomplete. The results have prompted scientists to investigate the possibility that inflation did not proceed exactly as currently understood, or that alternative models of cosmic evolution may be required to account for the discrepancies observed in the data. In addition to challenging established cosmological models, JWST's observations also suggest that the role of dark matter and dark energy, the mysterious components that make up most of the universe's mass-energy content, is more complex than we initially thought. While these entities remain undetected through traditional methods, their effects on the large-scale structure of the universe are undeniable.
Dark matter, for example, is thought to be responsible for the gravitational influence that shapes galaxies and clusters of galaxies. However, its exact nature remains one of the biggest unsolved mysteries in physics. Dark energy, which is believed to drive the accelerated expansion of the universe, has also become a focal point of cosmological inquiry. The discrepancy between the rate of expansion predicted by current models and the observed expansion rate, known as the Hubble tension, suggests that there may be unknown factors at play that we have yet to uncover. This tension between observation and prediction forces scientists to rethink not only the properties of dark matter and dark energy, but also their role in the evolution of the universe itself. One of the most exciting possibilities raised by JWST's findings is that the answers to some of these fundamental questions might lie in the properties of the very forces that govern the universe. For example, gravity, one of the four fundamental forces of nature, has long been described by Einstein's general theory of relativity. However, some researchers are now investigating the idea that gravity may behave differently at the largest scales, perhaps due to factors that we have not yet detected or understood. This potential revision of gravitational theory could have far-reaching implications for our understanding of cosmic expansion, galaxy formation, and even the nature of space-time itself. Moreover, as technology continues to advance, scientists are not only relying on the James Webb Space Telescope, but also looking to future missions and tools that will further refine our understanding of the cosmos. Instruments like the next-generation radio telescopes, gravitational wave detectors, and neutrino observatories will complement JWST's discoveries, providing a more comprehensive view of the universe from multiple perspectives. Each new piece of data obtained by these instruments will help piece together the complex puzzle of cosmic evolution. The challenges presented by these new discoveries reflect the inherent nature of science itself, an ever-evolving field that constantly re-examines its foundations in the light of new evidence. While the knowledge we gain today may not be the final word on the universe's origins or its ultimate fate, it brings us closer to answering some of humanity's most profound questions. As we continue to explore the unknown, the potential for discovery remains boundless, and each breakthrough brings us one step closer to understanding the vast, intricate cosmos we inhabit. Through these advancements, the future of cosmology is bright, promising new revelations that will reshape the way we think about the universe and our place within it.